In this last example problem, I would like to go ahead and walk through a heterodiatomic molecule rather than something that has two of the same element combining. And so I decided not to do hydrogen fluoride because the different N quantum numbers for the valence electrons is a little bit more in depth than I expect you to be able to do for our class. So we'll set that aside, and instead we'll focus on something that has elements in the same principal quantum number for their valence electrons. So boron and fluorine forming a bond. So first, a few things to note about something when we're combining the two. One, I'm going to note that fluorine is more electronegative than boron. That means fluorine will be lower in energy. Thinking about our periodic table on our second row, we've got neon and then fluorine and then oxygen and then nitrogen and then carbon and then boron. We'll go like that. And so remember, we have our divide between how the the sigma and the pi orbitals are relative to each other in energy. So if we're going to be combining fluorine and boron, we want to see what is the element that's in between those two directly, and we'll follow the rules for that one. So I can go 1, 2, and I'm at nitrogen, 1, 2, and I'm at nitrogen. So nitrogen is right in between boron and fluorine. So that means I'm going to follow the sigma and pi energy levels that I would for nitrogen. All right. So with that, I'm going to start building my MO diagram. I've got my energy scale, and I'm going to have boron, and I'm going to have fluorine. And my first step is to put in their atomic orbitals. So these are both going to be 2s and 2p orbitals for their valence electrons. And fluorine is going to be lower in energy. So I'm going to put my 2s here and my 2p here. And for boron, I'm going to make sure they're all at a higher energy level. So I might put my, and this is like relative, right? So maybe my 2p go here, and that would put maybe my 2s around here. I'm kind of guesstimating, right? It's just relative. We're not actually using measured energies or calculated energies here. So once I have that, I'm going to put in my atomic orbital diagram, like electrons. So for boron, it has 3. 1 in the P, 2 in the S. Fluorine, though, has 7. So quite a bit more. All right, let's build this MO diagram with these different energies. So my S orbitals are going to overlap and combine in a way that's going to form a bonding sigma orbital here and an antibonding sigma orbital right there. I'm going to move this just a little bit here. Make a little bit more space for myself. All right. So with that, it's important to also note that the bonding orbital right here is going to have more fluorine character because it's closer in energy. And that anti-bonding orbital is going to have more boron character because it's closer in energy to the boron. You can see like that boron atomic orbital and that antibonding MO are pretty close in energy, whereas the bonding orbital and the fluorine atomic orbital are really close in energy to one another. All right, so continuing to build this, remember I'm going to follow my nitrogen rule. So I'm going to actually have my pi orbital or MOs lower in energy than my sigma. So I'm going to put them in here. So there's my pi. And then I'm going to put in my sigma. And now I'm going to flip it. So now I need to have my pi, my pi anti-bonding orbitals, followed by my sigma anti-bonding orbitals. Okay, so now I have an MO diagram. And see, it looks a little different when these are offset in energy. I'm going to go through and fill my electrons. I have 3 from boron plus 7 from my fluorine. So I've got a total of 10. So when I make BF, I'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And so I'll fill those. So looking at this, I can tell right away it's diatomic. I'm sorry, diamagnetic. It is also diatomic, diamagnetic. That means it doesn't have any unpaired electrons. For bond order, that's going to be equal to, remember, my bonding versus my anti-bonding. So I have, I'm going to count out my bonding. I've got 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be equal to 8 minus, so let's count up my anti-bonding. I just have these two right here. So minus 2 divided by 2. So 8 minus 2 would give me 6, divided by 2 would be 3. So I have a bonding order of 3. That's a really close, tight bond that's going to be overlapping quite a bit. Or I mean, bringing them very close together. So it's a close, strong bond with a bond order of 3 that would kind of make us feel like a triple bond. And so that's how you can do these for these hetero diatomic molecules.